Welcome once again to my YouTube channel. Our today's topic will be on determination of specific heat capacity by electrical methods. Now, by electrical means, we can heat up a substance or substances. For example, we have electrical heater. When heat is generated from electrical heater to a substance, for example, you place kettle or maybe containing water on a burner, you will observe that the temperature of that very content in the container will raise. This is as a result of that electrical heater. So in that very case, the heat that will be absorbed by that very kettle will now be equal to heat supplied by electrical heater, provided there is no loss of heat to the environment. So in that very case, if electrical heater is used, then we have to consider electrical heat. And by electrical heat, we have this. The electrical heat energy, we have it as the product of power, that's the electrical power, and the time. Okay? So in that very case, I can now say that electrical heat energy, of course, we normally use H. We normally use H to represent heat. So electrical heat energy is the power, then times time. Now, the power is measured in watts, while the time is measured in seconds. So you should always consider their units whenever you are solving anything. So in this very case, if we have heat equal to power times time as a formula, then you remember that electrical power is the product of current and the voltage. So we have electrical power equal to current times voltage. Now, if you substitute electrical power here, which is the product of current and voltage, then you are going to have heat equal to IV, which is the power, times time. Then you have another formula for calculating electrical energy. Then again, from Ohm's law, then we have that current is equal to voltage over resistance. Then if you recall this very formula, we can make V the subject. We have V equal to current times resistance. Okay? You can still make R the subject. If you make R the subject, you still get another formula. So if we now consider I and the V, having this very formula, we can do the substitution here in order to get another form of the formula. So look at, in that case, we are going to have the current. When we substitute it in this very equation, we have heat equal to IVT. IVT, remember I is the current, V is the voltage or potential difference, while T is the time. Then we said that current now is equal to V over R. Now, if you substitute this very current here, then we are going to have heat equal to V over R times VT, right? So if you multiply this, you are going to have H equal to V squared T all over R. Then you get another form of the formula. Now again, if you consider this second one, which is V equal to IR, where we have V equal to IR, then if you do the substitution here again, you have V, you substitute V here, then we are going to have V equal to H equal to I times V, and the V here is IR, so you have IR then times T. So if you multiply this, you have H equal to I times I will give I squared, then RT. Then you get another form of the formula. So in this very case, in summary, you can now say that the electrical heat, this electrical heat, has variations of formula, which is power times time. It also has a formula, which we have here, IVT. It also has another formula, which is equal to V squared T all over R. It has another formula, which is equal to I squared RT. Now, all these formula will now be required whenever we are dealing with electrical heat. Now, from what is explained based on conservation of energy, we said when the substance got its heat from electrical means, we have it that the electrical heat loss, electrical heat loss will now be equal to what? Heat gained by the substances. Okay? So if we remember this, we have electrical heat here, where we have IVT, for example, which will now be equal to heat gained by the substance. Then we have the electrical heat, which is equal to the heat, which is equal to mc theta. We have this C as a specific heat. Okay, so the specific heat from what we derived from specific heat calculation, we have the heat equal to mass times specific heat times the temperature rise or temperature change. So if you make this very C the subject, you are now going to get the specific heat being equal to IVT all over, we have M, we have the temperature difference. So this is a formula that can be used to obtain specific heat once you consider electrical means. And then remember, this IVT has various forms. It can be IVT could be power times time. It could be V squared T over R. It could be I squared RT. It depends on the equation given to you. So with that, let's move into calculation. Okay, we have a question on the board. It reads, a 50-watt electric heater was used to heat a metal block of mass 5 kg. If in 10 minutes, a temperature rise of 12 degrees Celsius is achieved, the specific heat capacity of the metal is, we have option A, 50 joule per kilogram per Kelvin, B, 130 joule per kilogram per Kelvin, C, 390 joule per kilogram per Kelvin, D, 400 joule per kilogram per Kelvin. So in order to solve this very exercise solution, we have to write down the given parameters. Now we have 50-watt electric heater. So electric heater, we have the power given as 50 watts was used to heat a metal block of mass 5 kg. That's the mass of the metal block is 5 kg. So we have 5 kg. If in 10 minutes, that's the time 10 minutes. We have the time 10 minutes. A temperature rise of 12 degrees Celsius is achieved. So the temperature rise, that's the temperature change, is 12 degrees Celsius. The specific heat capacity of the metal. So what's the specific heat capacity of the metal? So in that case, we have specific heat capacity of the metal equal to, okay? So at this very point, we now have to simplify this following the principle of conservation of energy. So we said the electrical energy will now be equal to, that's the electrical energy loss, will now be equal to heat gained by that very substance, which is the metal block. So in that very case, the heat loss by heater will now be equal to heat gained by metal block. Now, heat loss by heater, we have power times time. That's the formula for heater, the energy of the heater. Heat gained by the block, we have mc theta, which is the temperature change. So at this point, we have the power measured in watts, the mass in kilogram, yes, while the time is in minutes. So we have to convert these minutes to seconds. Now, in order to convert minutes to seconds, we said 1 minute is equal to 60 seconds. So here now will be 10 times a minute is equal to 60 seconds. So if you multiply this, you are getting 6,000 seconds. So we do the substitution now. The power is 50 watts. So we have 50. We have the time as 600. The mass is given as 5 kg. Then the specific heat capacity is the one we are looking for. Then times the temperature change, which is 12 degrees Celsius. So at this point, we have to simplify. So 50 times 600, we have 30, that's 6 times 5, we have 0, 0, 0. That's the 30,000. So we have 5 times 12, which will give 60 times C, we have this. So in order to get the value of C, we divide both sides by 60, divide both sides by 60. So 60, we cancel 60. So our specific heat capacity, which will now be 30,000 divided by 60, is going to give 500. Now, what's the unit of specific heat capacity? Is joule per kilogram per Kelvin. So we have 500 as the correct option. So option A gives the correct option. So we have another question on the board. It reads, a calorimeter of heat capacity, 200 joule per Kelvin, and the mass 0.4 kilogram, contains water at 20 degrees Celsius. A heating coil of resistance 3 ohm connected to a 240 source is used to raise the temperature of the water to its boiling point, 100 degrees Celsius, in 5 minutes. Neglecting heat losses to the surrounding, calculate the mass of the water in the calorimeter. The specific heat capacity of water equals 4,200 joule per kilogram per Kelvin. Now, in order to solve this, we have to write down the parameters. So here, solution to the question, a calorimeter of heat capacity. So the heat capacity of the calorimeter was given as 200 joule per Kelvin, and the mass of 0.4 kilogram. That's the mass of that calorimeter. So this is the mass of the calorimeter, okay? So this is a specific heat capacity of calorimeter, mass of the calorimeter. It contains water at 20 degrees Celsius. That's the temperature of that very water, and the also calorimeter is 20 degrees Celsius. Now, a heating coil of resistance 3 ohms. So the resistance of the heating coil is 3 ohms connected to a 240 volt source. So the voltage of the source is 240 volts. Now used to raise the temperature of the water to its boiling point. That's the temperature of the mixture. You can just say the final temperature, okay? So the temperature, finally, the temperature of the mixture, we have it as 100 degrees Celsius in a time of 5 seconds. So the time now is 5 minutes. Then remember, you have to convert this time to seconds. So neglecting heat losses to the surrounding, calculate the mass of the calorimeter. Now, before we get the mass of this calorimeter, let's convert these 5 minutes to seconds. And if you do that, it will now be 5 times, well, a minute is just 60 seconds. So 5 times 60, which will now give us what? We have 300 seconds. So that's the time. So we have the specific heat capacity of that very water being equal to 4,200 joule per kilogram per Kelvin. Okay, now to solve this, we have to observe the principle of conservation of energy, a calorimeter of heat capacity, and the mass of water and the water. So you now see that the calorimeter and the water will now absorb the heat that will now be transferred by the heating coil. So in that case, we said the heat loss by the heating coil or by the heater will now be equal to heat gained by calorimeter, okay, plus heat gained by water. Now at this very point, we have the heat supplied by the heater. That should be electrical heat. Now we start with this IVT. Then the calorimeter will have the specific, we have the heat capacity given, not specific heat capacity. And if you recall that heat is equal to MC theta, that same heat is also equal to heat capacity times temperature change. Are we there? So in that very case, we are considering that of what? Heat capacity for the calorimeter, because we are given the what? The heat capacity of the calorimeter. So in that case, we have heat capacity of the calorimeter times the temperature difference plus the heat gained by the water is MC theta, because we are given the specific heat capacity of water. That's why we are using this very formula. So here we have electrical heat, we have resistance here instead of what? Instead of think current. So in that very case, we have to remember the formulas I gave. That's from the Ohm's law. We have to transform this very current into voltage and resistance. Then we know that current is equal to voltage over resistance. So if we replace this current with V over R, then we are going to have V over R times V. We give V squared over R, then times time, equal to specific heat capacity times temperature, the mass of the water, specific heat capacity of the water, temperature difference of the water. Now let's simplify. We are to find the value of this mass. Now let's do the substitution. Here we have the voltage as 240. So here we have 240 squared, then times the time. The time now is 300 seconds divided by the resistance, which is 3 ohms, equal to this heat capacity of the calorimeter is 200, then times the temperature rise. That's the temperature difference. The temperature of the calorimeter changes from 20 to 100 degrees Celsius. So the temperature change now will be 100 minus 20 degrees Celsius. Then plus, we have the mass. That's the mass of the water, which we are looking for. Then we have the specific heat capacity of the water, which is 4002. Then we have the temperature change, which is the same as that of the calorimeter, 100 minus 20. Then we simplify this, 240 squared, 240 squared, 240 squared, that will give 57600, okay, times 300 divided by 3 equals, we have here 200 times 100 minus 20, that will give 80. Then plus, we have the mass, okay, the mass times 42 times 100 minus 20, that's 80. So at this point, we multiply this times 300. Then we divide by 3. So here we're going to have 5760, then 000 equals 200 times 80. 200 times 80, then we're having 16,000 plus 4,002 times 80 times 80 times M. That gives 336,000 M. So in order to get the value of M, 1006, that's 16,000 will cross over, we have 576,000, then minus 16,000, then which will now be equal to 33,000 M. So when we subtract this, that's 576 zeros, 4 zeros, right? Then minus 16,000, that will give 5,744,000, which will now be equal to 33,000 M. So at this point, we have to make the M the subject of the formula, and to do that, we have 3 36000M equal to the 5744000. Hence, we divide both sides by 336000. Okay, divide by 336000. This will cancel out, so we have the mass. So let's divide now. 5744000 divided by 336000. So if we do the division, we are going to get 17.1. So we have it in kilogram. So that gives the answer to the question. So if what we did, we're able to help someone out there, please do subscribe, share, and turn on notification for others to learn as well. See you on our next class.